Thank you. I'm really happy that you invited me to do this. I've been at Nordita for 44 years, and that's roughly the period when the developments that we're going to hear about, that's when it all happened. So here's a little outline of what I want to say. First, a little sketch about the prize winners, have an interesting history, and then I'll talk about the work that won the prize, John Hopfield's model, and what's called backpropagation learning in layered networks. This is new to you. I'll explain what that means, which is what Geoffrey Hinton, his contribution was. And at the end, I'll take a little historical perspective of what led up to it and what happened since the work that was really responsible for the prize. So John Hopfield, he was born in Chicago. I just recently learned from looking things up on Wikipedia, his father is also called John Hopfield and was also a physicist. But John Hopfield Sr. wasn't born John Hopfield. His birth name, I think, was Jan Chmielewski. He came from Poland. And like many people who immigrated from Europe to North America in those days, including my own maternal grandfather, he changed his name for an English one. And that's how we know him now. So John got his PhD at Cornell, working with Overhauser, was a famous name in solid-state physics, working on optical properties of semiconductors. Continued that at Bell Labs in Berkeley, and in 1964 he moved to Princeton. And while he was there, he got interested in biochemical things. DNA proofreading was something that he made a real seminal contribution to. I think it might have been worth the Nobel Prize itself. But in biology, the computation is so stiff in these decades. Yeah. Okay, then he was in the physics department at Princeton, but this achievement in biochemistry got him a professorship in chemistry at Caltech. And I guess, also failed appointments in the other departments. And that was where he made this model that started all the noise. That's in 1982. He left Caltech and went back to Princeton in 1977. And he's still working. He's on extensions of that original Hopfield model, which are very interesting to us in the field. Geoff Hinton was born in Wimbledon, went to Cambridge. He tried a big variety of things to study, but he wound up with a degree in experimental psychology. Then, after a few years, he went to Edinburgh to do a PhD in artificial intelligence, one of the few places you could actually do a PhD in AI. And then he worked in a few places in Britain then, including this applied psychology lab in Cambridge. And I just mentioned that because my wife used to work in that lab. Well, it was actually when Geoff was in Edinburgh, but people remembered him because he'd done some work there when he was an undergraduate, and he came back there and worked there for a while, but he couldn't get a job in this field that he was interested in anywhere in Britain. But he found people to work with in San Diego, and he met especially John Rumelhart in the psych department. And that's where they invented backpropagation, the tool which is used to train basically all the networks you've heard about today. Not just here today, but all the stuff we read about. He got a faculty job at Carnegie Mellon, but moved on to Toronto, and he's been there since then. Okay, so what's the Hopfield model? Well, I like to give an example of an image processing problem. You have these patterns which are defined by these pixels, which can be, I'll choose them to be plus or minus 1, depending on.
I can move kind of. No, you continue as well.
Okay. According to whether it's shaded or not. Okay. And here's a messed up version of that figure. And the problem that you have is when you see a messed up version, you'd like to correct the errors and get back to this. And that's what this kind of model does. And it's very simple math, really. It's like an easy model in physics. So the energy is, for all the pairs, it's proportional to the product of their S's. So there's a minus sign out in front. So that means you get lower energy if the pair is either both on or both off, right? Both up or both down. And well, we have to specify what the J's are. In a ferromagnet, those are all positive, and I think you sort of understand how a ferromagnet orders, because the field acting on one of these is the sum of the product of these J's that connect it to all the others times those values. And so at the next step, just according to the sign of this, if I'm just looking at this without noise, no temperature in it, it'll just flip to follow the sign of H. Okay, so the question is, how can I choose these J's so that for some set of configurations, some set of these figures, it will, when presented with a messy version, converge to the right one. Okay. And that's easiest to understand if you look first at what I'll call the one pattern network. So there's one pattern which we call C sub 0, or super 0. And you just take the Jij proportional to the product of that pattern on the two sites, right? That just says that if those two sites, if they're both on or both off, this is a positive J, and if they're different, oh, it's a negative J. Okay, so if you, then the field acting on one of them in the presence of the others is this J0 times the values of the others. And suppose you put the other one, question?
Your Gij is symmetric in INJ or not?
These, yeah, these are symmetric.
And by definition, in the original one also.
Yeah. And if you put it in the state that you want to get to, right, this pattern itself, you plug that in for SI over there, then you just find that this field is just proportional to the state itself. And that means if you start in that, it'll stay in that state. So at least in that very narrow sense, that state is stable. And if you make a few mistakes, then some of these terms are going to be wrong, but they're going to be overwhelmed by the ones that are right. And so even local perturbations, it'll still converge to the right thing. Okay. And, you know, all this is just a ferromagnet in disguise. Right? It's just that instead of everything lined up together, the stable one is this pattern. You can even make a change of variables here that just turns it into a ferromagnet. Okay, so it's really trivial physics. What about when you have lots of patterns? And Hopfield said, well, just take this kind of term that you had for one pattern and add them up over all the patterns. And we're going to assume that these patterns are statistically dependent with their reason. Then when you calculate what's acting on site number I, if you started in state number B, you're going to get just like before, something proportional to that. Plus, so that's the B equals A term in the sum here. And then there's the rest of the terms, which are random numbers, because we chose random numbers to be these patterns, at least to have some mathematical problem to work with. And just from elementary statistical arguments, this is a random number with a standard deviation of order square root of the number of patterns divided by n, because we defined this thing with the size of the system and in the denominator. Okay, so in the simplest case, where you store a finite number of patterns, but take an infinite network, this goes to 0. So that's the sort of real purest Hopfield model that I can write down, and it can correctly restore all p of those patterns without any. Okay, so here's some examples where, what did we take? We took 7 stored images over this bunch of pixels. And this shows that a corrupted one evolves to the right one. A partial one also evolves to the right one, and so on. So that's associative memory recall. But,
so how did you train that middle one? You go for a Carlsberg to a Carlsberg and a two-board.
Yeah, but the stored pattern had the two different. Okay, so whichever part it saw, even if it saw a small part, it'd probably get it wrong because it's not correlated with any of the other stored patterns. Okay, this is just a one we did.
John?
Yeah.
Is there a relation of that if I give a fraction of the image, the time it takes to get the full image scales with something with the fraction?
Yeah, I think so, but I don't remember the details. I just want to get the basic idea across. Yes.
I actually don't understand what the iteration here is, because what you showed before, like the training is done on the clean data, right?
Yeah.
So you have all the parameters. So what is the middle image? Like,
it made part of the corrections, and then it made more corrections. So in 2 steps, it got to the right one. If you start with a noisier image, it may take more steps. But that's an important thing about this model. It's a dynamical system. And you're designing a dynamical system to do a computation. And that's sort of the novelty of this model and the approach that this takes. It's not like you have a dynamical system and try to understand it, but constructing a dynamical system using the ideas of physics. And that's why it's physics possible. Okay, so you can extend this, and one way that Hopfield did was, instead of just taking the spins I call them spins. So that's what we do in statistical mechanics. But these variables, the S's, instead of them being plus or minus 1, we could let them be continuous valued. And then the new value is this function of the weighted sum of the inputs. And typically for the G function, you take something like this. So if this was really sharp, it goes back to the old problem. And so you get the same arguments that I gave you. It gives you you get the same kind of results, except they don't have full strength, right? They're just value this G that solves this equation. And again, this is sort of like a ferromagnet at finite temperature. The G0, well, it's not quite right. The correct thing is that the derivative of G at h equals 0 has to be bigger than 1. This is true if you choose a hyperbolic tangent for G, which is okay. Now, what about non-zero temperature? Then we do statistical mechanics. And I don't expect you to learn statistical mechanics in detail yet. the takeaway message is that these S's have a Boltzmann distribution. That's the assumption you make. So these stochastic machines were introduced by Jeff Hinton and Terry Sajnowski. This is the simplest case of them. Again, if I take fully connected model, then mean field for this is correct. Mean field theory is correct. The simplest approximation that we make in physics. And it's a simple exercise to get a self-consistent equation for the strength of the memory. So how much these averages of S's overlap with the stored pattern. So you get this set of equations in that very simple case that I talked about. It's the same as the equation for a continuous unit model, like I talked about on the previous slide, if you choose the G function to be a hyperbolic tangent. Okay, so this was already talking about when I had a finite number of patterns and an infinite machine. But if the number of patterns you're trying to store is a finite, I'm using finite in the physicists' meaning of it, meaning non-zero, fraction of the size of the network, then that noise term, you have to include it. And that really leads to an interesting statistical mechanics problem that you can solve with methods from spin glasses, which go back to 2 years ago's Nobel Prize, which went to Giorgio Carisi. Okay, so finally, so why is this worth a prize? You saw it was something you had given a freshman stat mech course as a problem. Well, the new idea was that showing how it's possible to define a non-trivial, non-linear dynamical system to do a computation. So that's something new in life. It also shows that the principles and techniques that we use in physics can be extended to computational structures like this. So in physics, we think it's understanding the properties of matter. But we broaden our definition of matter here. So it's a new kind of matter, these networks that we make. Okay, so most of the excitement that you hear nowadays is about layered feed-forward networks, which are a different kettle of fish. So the simplest kind is just where you have a set of inputs, x, and some weights, and some nonlinear function that you take of them. Just like we were already talking about, you get an output. I can write a vector notation like that. And the learning problem that we have, which hasn't been discussed yet, right? In Hoffield's thing, he sort of guessed what the J should be and showed that it sort of worked. But here we're going to try and find systematically what the J should be, right? So we have many examples of what the correct, there's a true underlying J. And we get some examples of what the O's should be for them. So we have training example patterns, as we call them, with an index mu, label them. And for each one, there's a correct target. Okay? And we want this equation to be true for all these patterns, or at least we want to find the J that solves this smallest possible error.
The J is also free.
Sorry?
The J is also free. The J function.
Yeah, the idea here is to find the J function.
Here's to define the J function and G and J, both.
Oh, well, typically, yeah, when you make the model, you specify both the G and the J. But let's take a special case where you know what the G is and you want to find the J.
And in some cases, one can prove that the solution is unique.
Yeah. Okay, so anyway, a simple network like that, there was a lot of excitement about these in the early 60s, but then people realized there's certain things they couldn't do. So you had to go deeper. So here's one step deeper where the inputs are here, going to a set of what we call hidden units, and finally to the outputs there. There can be more than one of them. Okay, so the equation here is you take the inputs, take the weighted function here with the weights J1, which are those, take the G of that, and take the J2s, which are those connections, multiplying that, and the G of that gives the output. And you can do any number of layers. Here I just sort of tried to give you the general structure, but you could write this stuff down for yourself. At every layer, there's a bunch of J's acting on the output of the previous layer. Okay, it's a nested function of the inputs. And also of all the J's.
Sorry, maybe a small question. What is linearly separable? Can you explain that?
Oh, yeah. So I took this slide from somewhere else. Okay. Because of time constraints,
okay, sure.
I will not try and, but that means linearly separable are the things that a single layer thing can solve. Okay. I'll correct this slide the next time I give the talk. But real life problems are generally not soluble by just a single layer. Okay, so this is as much math as you're going to see. Well, almost. So what's backpropagation? This is the thing which made it all possible. And it was done by Jeff Hinton and some collaborators. And so it's really simple math. You define the error that you're trying to minimize as the difference between the target that you want and the output of the network squared, so that it's something positive. Sum it over all the training patterns. Okay. And you want to reduce the error. So you start with some random J's to start with. You want to reduce the error. So you just take the derivative of this E with respect to the J. And for that simple nested form, you can do that, right? Here's what you get when you do it for one layer. You get, first, you get this, then the derivative of the G, which is what the O is, and then the J times the derivative of the next one, and so on. So you get, in general, a sequence of things starting with the output error, going back with various powers of G, derivative of G, to these are the J's of the intermediate layer. And if you have more layers, there's more G primes and G's, more G primes and J's and so on. It goes backwards during the network, through the network. And that's why it's called backpropagation of the error. You want the error somewhere deep inside it. Start with the error output and just take these factors going back through it like this. And it's really easy to program. So why is this important? You see, this is a problem you could have given to a high school calculus student. Well, again, it's because it's an explicit prescription for constructing a nonlinear dynamical system that performs a desired computation. And just as I said about outfield models. And the thing that really is creating the prize is all the networks that you've been reading about in the newspapers that show such remarkable success, they've all been trained this way. So even if it was a simple idea, and actually some people thought of it before, but the papers they wrote were incomprehensible. These guys were the first to put it down and make it obvious and clear. And so then generations of engineers have been using it ever since.
John, but about this backpropagation, it's calculating the error so that you make in guessing the pattern? Or?
Well, you run the network and you see what the output is with the J's that you have.
Yes.
You see the error that you have.
to the pattern that you wanted. So you wanted, so you're comparing it to what you wanted.
Yeah, let me go back. See, here is the thing you wanted.
Yes.
This is what you got.
Yes.
So the first term here is always, first factor here is always the error at the output.
Right.
But you want to know how to change something deep inside the network.
Right.
So you've got to go chaining back through it by this algebra. Okay, so finally, I wanted to talk a little bit about, about the history, because these ideas go back, and people have been working on them for generations. Back, the idea of using variables to describe, they were thinking of biological neurons, but also computational neurons, one-bit variables. That goes back to the mid-40s. And as I mentioned, in the early 60s, there was a big excitement, work by Frank Rosenblatt, which was mainly with single-layer machines. You can do a lot of problems that way. But that ran into trouble because, people sort of knew if you added layers, it would help, but they had trouble training them because they didn't understand. I don't know, they didn't think of how to take this derivative, but you just saw. But so in 1969, and this is sort of where I came into the game, I was a graduate student. Marvin Minsky and Seymour Papert, who were computer scientists at MIT, proved mathematically that perceptrons can't do some necessary computations that you would have in practical life. And they argued, without proof, that multi-layer nets couldn't be trained. So that sounds a little stupid now, but it led to what we call the first dark age, where for 15 years, nothing happened. Except, Jeff Hinton was dreaming about this, even as an undergraduate. And when he and David Rumelhart and I forget who Williams' first name was, anyway, and also Jan LeCun, who's another famous guy in this field, they showed it wasn't hard to train multi-layer networks after all, as I just showed you. Okay, and that led to, in the ensuing 10 years, a lot of activity. And I was having fun doing it. But that ran into technical difficulties when you got beyond the second layer. These have now been understood and overcome, but it set us back. But more important was insufficient computing power, right? They just didn't have the mega whatever to do these calculations on big networks. Right? Little calculations you can do on this. So, well, this all changed in 2012 with what was called AlexNet, which won an image classification problem. There was a contest. It had been going on for a number of years with all kinds of methods people have tried, and every year the winner got a few percent better than the previous year. And suddenly these guys, with this network you see here, got like up by 50% better or so, something huge, which really showed that you could do something with these layered networks. Right, this one has 8 layers. Well, I don't want to go into too many details, but just if you're a physicist, you've heard of the renormalization group and how you use it to understanding what's happening at one scale from the smaller scale. So basically, these first bunch of layers are doing like a few steps of an RG calculation, if this means anything to you. But if you don't know renormalization group is, then just read this sentence. These are sort of hand-designed things. Well, with their connections in here, and those are trained as well. But they're arranged on successive length scales so that you can catch in the image the structure, the fine structure, and the more global structure, and so on. And then at the end, there's just a bunch of 3 layers of the general kind, like we were talking about before. Okay. Actually, Jan LeCun used this same architecture in 1989 to do a problem of recognizing handwritten digits. It's sort of like that first thing I showed you. And it worked, but he didn't have the computing power to do these big image processing problems. And so things were stuck for years. I should say these guys made one other innovation. Instead of a sort of smooth activation function, they use what's called a threshold linear activation function. So that's like this. And that seemed to help. The real key to the success was that they used graphics processing units. You know, these things developed for computer games, but they do fast parallel processing, which is just what you need, especially in these things. Okay. They use 2 GPUs in this thing. I mean, a real better picture of this is there's 2 of these things and they're connected a little somehow. So that was the key that made it possible for them to win the prize and set this whole field going. Maybe the people who invented the GPUs should be getting prizes. You know, in here I have 10 GPUs. And if anybody with a MacBook does, right? These days. But this was a big breakthrough then.
Great question.
Yeah.
Do we know what kind of scales each of these layers do the RG of, let's say?
Some of that's put in by hand. But you start with small fields and then they get bigger and bigger. And that's, yeah, there's a lot of kludge to this. But of course, you know, it had basically been they just had to copy LeCun. Okay, but this is what set off all the action. Okay.
Is there any improvement in looking in Fourier space? Because, you know, low frequency and high frequency is noise.
Yeah, there's tricks with these things with wavelets, if you know what they are. So it's a combination of its split scales, it's Fourier, like in the larger scales, it's localized. I mean, there's lots of details and people have tried all kinds of things. But I'm just trying to give a broad stroke picture of this. And yeah, so that's a detail that I can't go into here. So where are we today? Well, the biggest machine around is called GPT-4. It's the same basic architecture, right? It's feed-forward networks with 120 layers and 1.8 times 10 to the 9th connection weights in it in all. The training set, the number of examples it's trained on is about 1.3 times 10 to the 10th examples. It's just trained, sees a bit of text as the input, and predicts what the next token, as it's called, would be, and then you take that and feed it back in. Okay, so the previous one, you know, GPT-3, which is the basis for the first chat GPT that everybody talked about, was an order of magnitude smaller than this. Actually, this cannot go on because, did I say it on the next page? Yeah. Because there's not enough training data in the world if you go 2 orders of magnitude. And you can't train on the ones you generate by the machine either. That's cheating. Okay, so, but you know, people are working on this, and there's lots of ideas. This was just feed forward layer to layer, so there's no real dynamics in it, right? There's no feedback within the network. If there's feedback within the network, we call that a recurrent architecture. And I, for example, I'm working on some of those. There's also other ways of learning, what's called reinforcement learning, which is make the machine explore possibilities. So there's what's called the exploration balance. So if you just try to minimize things based on the experience so far, you'll get stuck. You have to occasionally make a guess outside that. And in reinforcement learning, you do that, you do these random exploratory dynamics, which is necessary to solve the problem. You know, this is a little bit less trivial than the feed-forward networks. It's hard to associate anything like our thinking processes with simple feed-forward deterministic thing. But if you put in a little noise, well, maybe noise describes a little about how we get new ideas at random or something like that. So maybe this will lead in a positive direction. What about quantum networks? Maybe people are trying to see what they can do. Will machines get smarter than us? This is a concern to both the prize winners. They've been public about this. If they get smarter than us, they might control us, according to Jeff. So they're worried. I'm not so worried at the current level of machines, but especially when we let in some randomness, it starts to look a little bit more like us. That's maybe a step toward what look more like how our brains operate, at least subjectively.
John, what does GPT stand for?
Let's see. General purpose something. I can't remember, but it's a.
I tried to Google it when I was listening, but I couldn't find it. You only see it's a word already.
I used to know this, but I can't remember.
He says that T is transformed and T is transformed.
G is generative.
Generated.
Pre-training transformer.
Okay. Pre-training transformer. Cool. Okay, good.
Okay, this is some details about how they train it. But at the level of resolution of this talk, it's basically backpropagation like that described. It's you know what it has another ingredient which they call transformers. What it is that at each layer, instead of just taking a weighted sum and feeding it forward, it does some statistical analysis of the input at that stage and feeds that forward. And that turns out to be very effective. Yeah, there's room for new ideas coming in every so often, and that turned out, like that prop itself, to be make a big difference in being able to do all this. Okay, so I think that's all I had to say. Thanks very much.